right, here's the kind of help to walk you through the calculated acceleration. So you have just gotten through watching the videos to kind of collect your data. And again, the sensor data should have given you position versus time graphs where you saw something that was curved. And remember that the A coefficient was equal to half of the acceleration. Or you could also make a comparison with the velocity versus time graph, and we were looking then for the slope of the line because the slope was also equal to the acceleration. So those are the two places where we're getting our experimental acceleration, and I would take these two values and I would average these values and make sure that they're put into your data sheets. Okay, so now off to the calculations portion of this. When we do the calculations, we're going to want to definitely look at each of the two objects and look at a free body diagram for them. So I'm going to start with the cart's free body diagram. So again, the cart's going to have some weight. Okay, so it has a force due to gravity. It's resting on the track, so in other words, there is a normal force. And the expectation is that the normal force should be the same size as the force of gravity. There's the tensional force that's coming from the string, and that's really the unbalanced force in this one. So the force of tension is going to be there. And we're going to consider this to be a very low friction cart, so we're not going to put a friction arrow into this free body diagram. Now the reality is there's probably friction involved there, and we probably should be including it, but it's going to make it a little more difficult for us to try to do that calculated acceleration if we had that friction arrow in there. So we're going to go through and we're going to set up our relationship. So again, the F of n is going to be equal to the F of g, and the unbalanced force, the net force, is just equal to that force of tension. So that's our force of tension, and that's our free body diagram for the cart. Now the hanger, on the other hand, is going to have a different free body diagram. It's going to have that tensional force. In fact, that tensional force is going to be the same size as it is in the cart because it's the same string running through it. So this force here is the same size as that force there. So the tensional forces are the same. Now the hanger, though, has to have a force of gravity that's greater than that force of tension. Okay, and so this is what's going to happen is we'll get an unbalanced set of forces that's going to act down. So again, the F net on this one is going to be equal to the Fg minus the F of t, so our tensional force. Again, this is our cart, and this is our hanger. Okay. Now when we start to look at how to solve or how to work with these equations from a free body diagram, we're going to use what Newton said about the net force, is that the net force is always equal to the mass times the acceleration. Now remember, though, that this is the mass now of the cart, not the mass of the hanger. Okay, so we're just really doing a replacement here and getting rid of the net force with the MA relationship, and then that'll be equal to our FT. When we do the same thing over here, again, that M is going to be that hanger's mass times that acceleration is going to be equal to that. Now we're doing a replacement for the F of g, and that means that we're going to have an MH, so all F of g's are just equal to a mass times gravity minus the F of t. Now what happens here is this acceleration and this acceleration represent the acceleration that we're experiencing through our Atwood's machine, or between the cart and the hanger, and that acceleration has to be exactly the same. So that's the calculated acceleration that we want to get, and that's the one that we're comparing back to the acceleration from our experiment. So we're going to do a replacement here because the F of t represents the same thing. So I'm going to take this piece of information and I'm going to substitute it over into there for my F of t. So I'm really going to have now MHA equals MHG minus MCA. And what we now need to do is get the acceleration's on the same side. So I'm going to add that over to the other side. So I'll get MHA plus MCA equals MHG. And now I'm going to do a quick little reduce, or I'm going to do a undistributing or a factoring step here, where I'm going to take the A out so that the A is now equal to the MH plus the MC equals the MHG, and then we just divide by that quantity. So these cancel, so really our A is equal to this right here. And so that means that if we can take the masses from our experiment, take gravity, which is going to be 9.8 meters per second squared, we should be able to get this acceleration and then make a comparison. When we make a comparison, we are doing this in terms of a percentage error. And remember that percentage error is always equal to your experiment minus your calculated. We're going to do absolute values of those, and we're going to choose one of these two, because really this isn't a percent error, it's a percent difference. So we'll treat the calculated as our accepted type 1, so it's going to be experimental minus the calculated divided by the calculated times it by 100, and that's how we'll look at our percent differences. Okay? So if you have other questions with this lab, go ahead and ask them, but this should be able to get you through so that you can complete the calculations portion.